So we're going to talk about vector addition. Now, to help us guide through this wonderful endeavor, I'm going to make some atrocious drawings, so please don't judge. And the worst thing is I actually can draw, just not like this. I don't know why. So here's an aircraft carrier, all right? And then you've got a plane on an aircraft carrier. We'll call that a plane. Sure. All right, plane aircraft carrier. Now, a plane wants to take off from the aircraft carrier. In order for a plane to be able to fly, it has to reach a certain speed. Now, out in the ocean, you have wind. So you've got the velocity of the wind. And I don't know if you know this, but whenever they launch the planes, here's the velocity of the aircraft carrier. Whenever they launch the planes, they always want to have it so that the aircraft carrier is going straight into the wind. Well, why do they do this? Well, because vector addition. So whatever the speed of the aircraft carrier is, plus the speed of the wind, well, that's the total velocity bonus that the airplane's getting. So that means it's easier for the airplane to get up to speed because relative to everything else, it's already moving. Okay? Now, if we were to reverse this and aircraft carrier, all right, airplane. This is a worse airplane. It's almost falling off the end. Let's say that this time the aircraft carrier is going again or with the wind. So aircraft carrier, but now the wind's going this way. If you look relative to the wind, it's basically keeping up with it. This is like being in a car and you're going the same speed as the car. You don't really notice the motion. So relative to you, it's not really working. So here, because they're in the same position, your total is basically going to be a big fat zero. You're getting no assistance to that airplane by moving off because you are moving with the wind. The wind is not going to help aid in this speed that you're trying to reach. So we have to look at how the vectors work together relative to each other. So here, these two vectors are in the exact same direction, so there's no difference between them, so we're not getting any gain. Here, these two vectors are working against each other, so we're getting a gain. So this way, if the airplane tries to take off, this airplane is going to have an easier time taking off than this airplane would have. All right? So that's pretty much why they do what they do. So we're going to add vectors together. So that's just a conceptual thing, relative motion, things like that. Let's do an actual type problem you might run into. So let's say that we've got an airplane that's going to land. All right, so I'm going to now draw again another bad airplane. I swear I can draw. All right, airplane, I don't know, airplane. We'll do this. It's got some wings on it. It's got extra wings. Drawing fighter jets apparently. All right, there. So you've got this. It's a better airplane. Still not quality. All right, so you got like a fighter jet here. So let's say it's going to land. All right, but there's a problem. We've got a crosswind. All right, so if it's on an aircraft carrier, they can just change the boat. Like the boat can point in a different direction, so they don't have to worry about this nearly as much, unless it's like a storm. But if you're going to land on the ground, sometimes, well, the runway, is like this, but you've got a crosswind of, say, I don't know, 40 miles an hour going like this. So therefore, you've got to deal with those two things working against each other. Now, in order for the airplane to land, it has to go straight. So it has to try and compensate for this 40-mile-an-hour crosswind. So what does that mean? Well, normally when an airplane lands, I looked this up, they're traveling about 150 miles per hour. All right, and you've got this 40-mile-an-hour crosswind. So, well, how are they going to deal with this? Well, to compensate, you have to do some vector addition. So they're going to go and they have to cancel out that 40, just kind of like how we canceled out everything up here with the aircraft carrier. They got to cancel out that 40. So they actually have to match their speed to go 40 miles per hour against that crosswind, but they're going to keep their speed of 150 miles per hour horizontally. So they actually have to land at an angle. So if you've ever seen a video or something like that of one of those, Boeing 747s or whatever, they're landing, sometimes they land at an angle because they have to compensate for that crosswind that's going to push them off course. So we can just simply figure out, okay, so I had to cancel out the 40. I draw my new triangle to find my vector. So then I can figure out, okay, well, what is this angle? Well, to figure out the angle, you can say, well, tangent of theta is equal to opposite over hypotenuse. Make sure you're in degree mode. And you basically say, okay, so I've got to land at a 15-degree angle. All right. Now, not only do I have to land at a 15-degree angle, but I also have to change my speed. All right. So you got to figure out, well, what's the hypotenuse of that? So you can say, well, V equals 40 squared plus 150 squared equals V squared. A squared plus B squared equals C squared. No problem. And you can say, well, okay, how fast do I have to go? Well, if you crunch those numbers, you have to go about, I'm rounding here, 155 miles per hour. So in order to actually land on this straight runway and compensate for the 40-mile-an-hour crosswind, you have to turn into it, and you'd have to land on the ground at a 15-degree angle, traveling at 155 miles an hour instead of the 150 that you wanted to. So that's why it's not so easy to land an airplane as we might think. But that's basically vector addition. All right. So you evaluate the situation, draw a bunch of arrows, add them all up, figure out your angles, stuff like that. So I hope that was helpful. And I guess I'll see you guys in class.